So there are four special processes that we're going to pay attention to in terms of the thermodynamics that we're going to do. The first is called an adiabatic process. And for an adiabatic process, no energy is transferred into or out of the system as heat. So for an adiabatic process, Q is going to be 0. So first question becomes, well, how can a process be adiabatic? And there's a couple ways that you can do this. One is you can keep the system isolated, which means that there's no pathway for the energy to be transferred into or out of a system. Or the process can happen so quickly that there's not enough time for the energy to be transferred into or out of a system. So adiabatic processes tend to be either you've got your system insulated in such a way that heat doesn't flow into or out of it, or you do something so quickly that heat can't flow into or out of it during the time the process is going on. The second process is going to be an isochoric process. And so this is a constant volume process. So we'll use isochoric interchangeably with constant volume. They mean the same thing. What's important about an isochoric process is that if the volume remains constant, then no work is done by the system on its surroundings. So the work term in our first law of thermodynamics is going to be 0 for an isochoric process. The third process is an isobaric process, and isobaric means constant pressure. So in the same way that an isochoric process is constant volume, isobaric is constant pressure. And this also tells us something special about what's going on with the work done by the system. So if the pressure remains constant, then the work done by the system is easy to calculate because our work done by the system was an integral of PdV, but if that pressure is constant, we can pull it out of the integral and I'm left with just whatever the pressure value is at my constant pressure process times the change in volume. This is just the area of a rectangle on a PV diagram. So it's easy to calculate algebraically. It's also easy to calculate geometrically from the PV diagram. Our last process is an isothermal process. So this is a constant temperature process. Well, how can a process be isothermal? Again, we can sort of imagine how you keep the pressure constant. We can imagine how you keep the volume constant. How do you keep the temperature constant? Well, the easiest, sort of by definition, for something to be isothermal, it means that the system must remain in thermal equilibrium. And so there's, again, sort of two things that have to happen here. The easiest way to do it is basically to put your system in contact with a thermal reservoir and then transfer the energy into or out of the system very slowly. So this is known as a quasi-static process. It's not quite static because things are changing, but they're changing so slowly that basically you can keep your temperature the same because you'll take whatever energy you need to or dump whatever energy you need to into the thermal reservoir so that your temperature stays constant. So if we think about how these processes, sort of summarizing them, right? So the four that we're going to sort of focus on: adiabatic, isochoric, isobaric, and isothermal. And again, adiabatic means that your Q is 0, no energy is transferred into or out as heat. Isochoric is constant volume, isobaric is constant pressure, isothermal is constant temperature. And so what this is telling us is that for adiabatic, we've got Q equals 0. For isochoric, the work done by equals 0. For isobaric, the work done by is easy to calculate. And for isothermal, the temperature is going to be 0. And so if you look at this, you say, well, there's something going on with Q, there's some things going on with work, so this clearly indicates that there's sort of some special situations for these processes in terms of the first law. And so when we think about how these processes sort of affect the first law, well, for an adiabatic process, and if Q equals 0, so the first law of thermodynamics is that the change in the internal energy of the system is equal to Q minus the work done by. So it's keeping track of the energy taken in by the system or given up by the system as heat, and then it's keeping track of the energy that's being either transferred into or out of the system through the system doing work. Well, for an adiabatic process, if you make the Q term 0, then you're left with a first law that says that the change in the internal energy of the system is equal to negative the work done by. So what this tells us is, well, I know that if I have an expansion, then the work done by my system is going to be positive. Right? So the system has to do positive work to expand. So if my system expands, then the work done by term is positive, but this minus sign tells me that the internal energy has got to decrease. So the internal energy of my system will decrease during an adiabatic expansion. On the other hand, if the work done by is negative, which is another way of saying that work was done on the system to compress it, then I'll have two negatives that'll cancel and leave me with the fact that the internal energy increases. So during an adiabatic compression, the internal energy of my system is going to increase. For an isochoric process, so again, I know in an isochoric process that the work done by is 0, right? There's no work done by the system because it doesn't expand. There's no work done on the system because it doesn't compress. So the work done, my work term in the first law is going to be 0, which tells me that the change in the internal energy of my system is equal to the energy transferred into or out as heat. So this means that, again, if I have a situation where I add energy to the system as heat, Q would be positive, which means the internal energy would be positive. So for an isochoric process, all the energy added to the system as heat goes into increasing the internal energy of the system. That's isochoric heat. Right? So none of it goes to doing work. All of it goes directly into changing the internal energy of the system. On the other hand, if I remove energy from my system as heat, that means that all of that energy that was removed is also being removed from the total internal energy of the system, so that all the energy that's removed from my system results in decreasing the internal energy if I have isochoric cooling. Well, I've got an adiabatic process to get rid of Q. I've got an isochoric process to get rid of the work term. Wouldn't it be nice if we had a constant energy process so we could get rid of the change in energy? So for a constant energy process, and we'll talk about special situations in which we can actually easily see constant energy processes. But for a constant energy process, what this means is, you take the work term over the other side, it tells you that the energy transferred into or out of your system as heat has got to go into work being done by the system. So you don't do anything to change the internal energy. So if you take in energy as heat, in order for the system's total energy to remain constant, everything that you take in must immediately go into making the system expand. So you know that Q would be positive. You need the work done by to be positive. That means your system has to expand. And so all the energy that you take in as heat is basically immediately converted into doing work by the system as it expands. Well, on the other hand, let's say that you do work on the system. So you're doing positive work on the system means that the work done by term is negative. So when you compress the system, work done by is negative. And so to keep the energy constant as it's compressed, all the work that you do on the system has to be dumped out as heat. So basically, you, in compressing the system, you're trying to add energy to the system. In order to keep the internal energy constant, the system has to take all that energy and dump it out as heat so that it keeps the total energy constant. So what we'll see is there is a particular process when we're dealing with a very simple system, like an ideal gas, that gives us a constant energy process. And so that's part of what we'll build up to next, is talking about that simple system and talking about thermodynamic processes with that simple system.